Fundamental units of crystalline solids. Before we delve further into the solid states, we will try to understand certain basic fundamental units of crystalline solids that will help us to better understand the overall behavior of crystalline solids. Bravis lattice. What is Bravis lattice? Bravis lattice is an infinite array of discrete points generated by periodic arrangement of motif. So it is an infinite array of discrete points generated by the periodic mean. You see, after some time it repeats itself of the basic motif. Unit cell. Unit cell is the smallest portion of a crystal lattice that repeat in a different direction to generate the entire lattice. For example, we having here edge lengths A, B and C. These are the usual dimensions, edge lengths, and here we having three angles between counted such like that. Between A and C it will be beta, between A and B it will be gamma, between C and B it will be alpha. So we can consider alpha, beta, gamma is opposite to A, B and C. Whatever is missing, if A and C it will be beta, if A and C beta, A and B gamma, C and B alpha. Unit cells can be broadly divided into two categories. First is primitive unit cell. Primitive unit cells are those that have atoms or ions only on the corners, do not have any atom or inside it or on the faces of that. This is a primitive unit cell having the constituent ions atoms only on the corner. Next is, and now all the primitive unit cells, how many atoms are there per unit primitive unit cell? How will count? Each cube unit have 8 atoms on the corner, and each corner is shared by 8 different units. Like here you see this corner, one is here on right side, one is on its, we can see top of it here, one is this corner. So 4 units are here, 4 units here will share the same atom, and this here. Similarly, here will be top 4 more units on the top of it that will also share this corner atom. So basically, single atom corner is shared by 8 primitive units. Thus, it means the contribution of a single atom to each unit is 1 by 8. And how many corners are there in a single primitive cell? It's 8. So 1 by 8 into 8, we are getting 1 atom per unit primitive cell. Is HA, which is equivalent to 2 radii. Here we see 1 radii, 2 radii, and all atoms are identical. So it means, and they're touching each other, it means A is equal to 2R. Volume occupied by the atom is equal to 1 atom per unit cell into 4 by 3 pi r cube. That is it. Total volume occupied by a single atom. What is the volume of unit cell? It's A cube. So volume of a atom, volume of cell, it will be 4 by 3 pi r cube. Now here a cube, which is a unit volume, means 2r cube, 8r cube. So if we'll calculate it, it will be coming out roughly 52.4%, which is a packing efficiency of primitive unit cell. Next is centered unit cell. There are two categories, because in centered unit cell the atoms can be present inside the body here or on the faces like here. Obviously along the corners all atoms, constituent atoms will be there. Let's see body centered first. Body centered unit cell having a atoms on the corners as well as in the center of the body. So here we see one constituent particle at its body center and each corner having a 1/8 of atom. Total will be 1 at the center plus 8 1/8 at each corner, 1/8 into 8 corners. So 2 atoms per unit body centered unit. Now how to calculate the packing efficiency of a body centered? We know it's the volume of the atoms by the volume of the unit. Radius of sphere is r, side of cube is a, and we having a body diagonal here running across a unit cell. This is the body diagonal. It's because all atoms are identical. It will be r here, 2r here, body centered, and r here because it's touching. Total will be 4r. Body diagonal size is 4r. Now let's calculate it in terms of our edge length of unit cell. It's a, and this side is also a. So this diagonal will be, we have to calculate it according to Pythagoras theorem. It is nothing but a square under root 2a. We having here another edge length. If we have to calculate the body diagonal from here to here, it will be like under root 2a square plus a square under root again. So mean under root 3a. This length is under root 3a, which is equal to 4r. We already saw it. 4r. Under root 3 is equal to 4r. So a will be equal to 4 by under root 3. Now let's calculate the packing efficiency. We know there are 2 atoms per unit cell. So it will be 2 into 4 by 3 pi r cube divided by a cube, which is 4r under 3 cube. If we calculate this, packing efficiency comes around 68%, which is higher than our primitive unit cell. So body centered unit cell having a packing efficiency 68% compared to 52.4 in primitive unit cell. Next again, face centered. Such a units having atoms at the corners as well as on each face. So each face we know here this atom on the faces are shared by only 2 unit cells. So means 1/2 comes to each unit cell. Here are 6 faces of each unit cell. 6 into 1 by 2, which is mean 3. 8 corners, 8 into 1 by 8 means 4. So each unit cell will have 4 atoms in case of face-centered unit cell. Let's calculate its packing efficiency. We know edge is A, so face diagonal will be equal to under root 2, we already know. Compared, if we see this face length, it is again 4R, R, 2R, R. So under root 2A will be equal to 4R here. That's what we know. So A will be equal to 2 root 2R. Total number of volume of unit cell A cube. To calculate the packing efficiency, 4 into 4 by 3 pi R cube, which is the total volume of that atoms divided by volume of unit, which is 2 root 2R, and its packing efficiency will be equal to 74%. 68% we saw in body centered. It's still higher. So we know any solid that is having a face centered unit cell as a basic unit of three-dimensional crystal arrangement, having a higher density compared to our body centered, and body centered in turn will have higher density than simple primitive unit. That's what we saw. So how to calculate the density of a unit cell? It is total mass present divided by the volume. So what is the mass present in each unit cell? It is the mass of atoms, which is mass of atoms, volume of the unit cell. Mass of unit cell is equal to number of atoms present into mass of a single atom. So it will be equal to Z, which is the number of atoms present, M is the mass of single atom. We know single atom masses will be equal to molecular weight in grams per mole divided by Avogadro number. So we substitute here, mass of an atom will be molecular weight or molecular mass divided by Avogadro number, which is 6.03 10 to the power 23 Zm A3Na. That's how we calculate the density of a unit cell. And if we, whatever of known, this is known, Avogadro number is known, unit length we can found experimentally. This we know from the arrangement. So density of a unit cell can be found. Or if we know density of a unit cell, if we know the density, if you having a assumption that density is uniform throughout that crystal, then using it we can find the molecular weight also.